Holiday and Resnick, chapter 25. We're still working on capacitors. We have a parallel plate capacitor with area 10.5 centimeters and a plate separation of 2D, which is 7.12 millimeters. The left half of the gap is filled with a material that is K equal 21. The dielectric constant is 21. The top right half is filled with a material dielectric 42. And the bottom right half is filled with a material of dielectric constant 58. Okay, what is the capacitor? Well, what we have is, if we were to draw this out in a circuit, we'd have one capacitor over here. And on this side, we would have two capacitors, and we would be computing the equivalent capacitor. So it's the same thing. So this is what we're going to do. So if you figure out that plate area, to get it in meters, it's going to come to 1.04 times 10 to the minus third meters square. That's the plate area. And we need 1/2 of it. We got 1/2. So 1/2 of A, plate area, is going to equal to 5.25 times 10 to the minus 4. So this is the formula we're going to start off. C1 for capacitor 1 is going to equal to K1 over D times epsilon naught A. This is going to equal, K1 is 21 times 8.85 times 10 to the 12 times 5.25 times 10 to the minus 4 divided by the distance, which is 0.0712. That's going to equal, and we're going to come back, we're going to write them all out, then we'll solve them. So K2, so C2 is going to equal K2 epsilon naught A, and we got 1/2 D now. In this case, 1/2 of D. From here to here, it'd just be 1/2 of 2, so that's just 1/2 of the distance. It's going to equal, K2 has a value of 42. 42 times 8.85 times 10 to the minus 12. Minus 12 times 5.25 times 10 to the minus 4, and it's just half the distance now, which would be 3.56 times 10 to the minus 3, and that's going to equal, and we're going to do K3 here, so C3 is going to be K3 epsilon naught A over 1/2 D, and K3 is 58. So we have 58 times 8.85 times 10 to the minus 12 times 5.25 times 10 to the minus 4. And it's just 1/2 of D, so that's 3.56 times 10 to the minus 3. And I'm just going to change this, correcting it at the same time, to 7.12 times 10 to the minus 3. This D should be 7.12 times 10 to the minus 3. Okay, I'll be back and with the calculations on that. So when you do your math, C1 is going to be 1.37 times 10 to the minus 11 farads. C2 is 5.37 times 10 to the minus 11 farads. And C3 is 7.41 times 10 to the minus 11 farads. Now these two capacitors are in series. So to get an equivalent on these two capacitors, we're just going to say C equivalent for 2, 3. It's going to equal the product divided by the sum. C2, C3 divided by C2 plus C3. And that's going to equal 5.37 times 10 to the minus 11 times 7.41 times 10 to the minus 11. And on the bottom, we're going to have 5.37 times 10 to the minus 11 plus 7.41 times 10 to the minus 11. And I'll pause and I'll do this calculation. That's going to be 3.17 times 10 to the minus 11. Now all we have to do to get the equivalent capacitance, since these now are parallel, this is what we have. We have now two parallel capacitors. This one's going to equal 3.17 times 10 to the minus 11. This is capacitor 3,2. This is 3,2, 3. And on this side, we have a capacitor of 1.37 times 10 to the minus 11. And when we add these two, we're going to get 1.37 plus 3.17 equals 5.54. So our capacitance, C equivalent, is going to equal 4.54 times 10 to the minus 11 farads. So all we did, we got the area of the capacitor, and then we multiplied the capacitance by their dielectric constants. And then we had a series here, which we converted to a equivalent capacitor. And once we got that equivalent capacitor, When they're in parallel, all you do is add. So we just added this capacitor to that capacitor, and we got an answer of 4.54 times 10 to the minus 11 farads.